Good afternoon, everyone. It's sure it's been a long day already. So we'll do this over the course of an hour. I think it's not going to be the full hour and a half. I'll try to keep it interesting for you. So this is an IES presentation of energy modeling and data analytics for net zero retrofit. So it's myself, I'm Giulia, I'm our R&D Operations Manager, and Johan, the head of sales in Europe. So we're here to present some practical things and software solutions applied to the retrofit case specifically. So without further ado, let's start from the basics, right? You know, retrofitting is a big part of our future. All of us know this. 80% of existing buildings that will be there in 2050 are already around today. And there won't be many new buildings coming. You know, its existing buildings are going to drive carbon consumption, energy consumption, and resource consumption. And that's a huge challenge, no matter where you are. There's been retrofit targets set over many years now. We know we need to reach 3% of renovation at the global level, but probably at 1% if we're lucky. So there's a lot of challenges there and why that's not happening. So what we're trying to do in IES is working with companies and partners, is enabling and empowering building owners to identify the best means to retrofit. And that means doing it at the lowest cost and maximum impact throughout the whole life cycle. So you have the building as a physical asset, but now we also have the digital asset. And the conversation today is about how we use those digital assets through the life of the building. So this is the whole approach, right? It's a bit tiny, I hope you can see it. So basically you have, once a building is constructed, there's 4 steps over the whole life of the building that we're talking about here. So the first one, the building is constructed in operation. It's brand new, 20, 30 years old. There's some gains to be made on the existing building. So the first thing is examining the operations of the building. Where's the low-hanging fruit? Can we look at the systems, make sure they're correctly set up, there's no faults in how buildings should be operated. Then we start integrating information in the digital asset, right? So how do we bring that information in? How do we renovate or retrofit? What interventions do we apply? Could be small, quick wins, or it could be big capital expenditure. And how to do that depends, it's always going to be different by user, by use case, by customer. Every user is different, every operation is different. So basically the assets we're looking at are individual, they're dynamic, they're changing. So once the retrofit or optimization strategy is complete, then the building's performance is improved because it's a dynamic entity. We need to monitor it and ensure we continue that improvement. So we need to verify that what we're implementing is actually delivering on the outcome that we intended. So we have to then be able to do post-retrofit commission and evaluation and monitor and track the performance of that building and the interventions that we applied. So what I will do today is I will go through all of these steps with examples of things we do in IES as part of the approach, the tools that we use, and how we go on about it. But maybe before doing that, just a bit of a conversation, a bit of moment for the room to think about. Do you think are the biggest challenges on the decarbonization of the built environment? Like, we do have some opinions on this, talking from our clients, our customers, our R&D partners, and what we do in IES, but I think it's good to get that. So if there's anyone want to answer that question? So no, it's a no judgment zone.
Transparency.
I do transparency.
What's going on in the building? So is anything monitored?
Yeah, data, information. Yeah, it's a good one. Yeah.
Or lack of documentation actually in existing buildings.
Yeah.
So yeah,
that's a good one.
Starting point.
Yeah. Anyone agree? Anything else on top of that?
A fragmented context where there are too many stakeholders and each one is minding his own part, and there's not an overall perspective that can be focused on solving the real issue.
That's a good one, yeah. Fine.
Old building stock,
Yeah.
protected facades.
That's another good one, yeah. Project limitations. Hell yes, story, yeah.
I think it's also a matter of educating the client about how it's beneficial for them to work on the retrofit.
Yeah. What does the owner get out of it? It's a difficult question to answer. So they're all good, yeah. I think kind of covers, I had the costs, because it's also how much are you willing to pay for it? Cited. The project limitations, so history, technology barriers, the skills gap, understanding, like, also there's so many stakeholders, but there's also not understanding of what the building performance is, the access to data, and then the behavior of the occupants of a building and what they do. Like these are the ones that I had noted down. So it's good to see that we're about on the same page. So it is roughly what it will cover. So the first bit is then optimizing the existing performance of the building. So the first stage, and I'll talk a bit about the processes and those challenges that we touched upon that we all understand are the biggest ones here. So the first one is what we're saying is understanding the buildings, massive challenge. And it is specifically an issue, as we all know, because each building is different and different fabrics, different controls, different technologies. The one thing they have in common is that they don't get to the performance expectations usually. So there always are potential to quick wins, operational savings gained by just understanding the building better. And so the accuracy, that transparency you mentioned, yeah? Having that accurate data on the building consumption is essential, because then with that we can establish baseline pattern of consumption, compare it against benchmark, just understand, is it doing well, is it doing poorly? Then after that, we can go in and make low or zero cost interventions and controls that help save money. Then that money can be reinvested into capital expenditure and ultimately increase the impact of future retrofitting measures. So one thing that we do is to understand the buildings better is use our software, it's iScan, which lets us grab different data sources and then be able to interrogate that data to try and visualize the patterns and try to understand what is going on in the building. So just to summarize on this common challenges specifically on the data, that limited building information, right? We often encounter paper copies of schematics, like for mechanical electrical systems, or sometimes they're just nothing. There's documents that are dated 10, 15 years old. There's outdated as-built documentation. And BMS systems, if there's any, may be old as well, or have limited data, or the data is there, but it's not stored permanently, and it's lost, like it's overwritten every 10 days. That's a common issue. Or you may find, there's data, but you don't know what the sensor is. Sometimes you just get a temperature sensor one in the BMS, you don't know what it is. It's a lot easier in newer buildings. They have better naming conventions, they have longer, the BMS are more like newer generations, they have longer trend. But even on the metering side, in older buildings usually have granular, they don't have granular data. So maybe it's just 1 meter for the whole building. We have older buildings with meters that are not installed. They're not connected to the BMS, so we cannot get the data out. So in newer buildings, it's a lot easier. So in our experience, that's mostly the primary challenges we have in older buildings. But so what we tend to do, and this is based on the best practices of our consultancy team using our software as well. So the first thing is starting in an existing building, starting from the BMS, if there's one, understanding what's going on. So the first thing is there any usable data? And that is a good challenge. So first, it usually isn't. So you need to discuss how to acquire that data. Because then when the data is accessible, there's some clear representative data Then we can go on and decide what additional data is required. So that depends on the project scope. So are we looking at the energy? Then meters may be sufficient. Do we want to look at thermal comfort? Then we're going to need zone sensors in the zones. But the important thing here is, first of all, knowing what you want to do, and then identify and go and get data points. So if the data is there, then yeah, we can usually can be exported in CSV format, which then can be imported into iScan, and I will show you an example of that. And this is a manual data process, but of course, there's another method which is automatically gathering the data. So the same flow, but there's more direct connection into it. And so what we do in those cases, in those more advanced cases, when that automated connection is possible, we actually can connect live data in iScan. So connect to the BMS using email, MQTT APIs, depending on what's available. So that is, in our experience, the better way to connect for a longer decarbonization pathway, because then what it enables you to do then is you constantly can see the effects of changes you make on building operations, instead of actually every time going back and manually getting the data, grab it, and analyze it. So in terms of supporting documentation, right, even if there is data, then we also need some documentation to help understand the data better. So, for example, we will look at the description of operation, so how the BMS was originally designed to operate, right? Because then that can be used to compare against how it is actually operating and running the building. Any available manuals on operations and maintenance to help that understanding. If there are available, these are very useful in our experience, as installed or as built schemes for mechanical and electrical systems to help understand the energy flow. And that as built is key, because usually the design doesn't reflect what has actually happened in the building. So it's important to start off with the right foot. So commissioning maintenance sheets may be very helpful to identify if there's broken valves, sensors, there's issues, and so on. So it's all about better understanding the building, and this is the best starting point. But so basically, once that's done, having the data, having that core documentation, we can put it into iScan. But before going in and doing that interrogation, there's a few good basic practices that need to be put in place. It's like, runners starting marathon. First thing is you tie your shoelaces, or you're gonna fall on your face. So that's the same for decarbonizing a building, right? The first thing is always start with the basics, starting from the identifying the faults. Is there issues in the boiler, the pumps, the sensors? Like those are very common. There's comparing the schedules. So what's the operational schedule of the building? What's the BMS operating schedule? Do they match? There's often a mismatch there, and cheapest and greenest energy is the energy you don't use. So there's often operational costs savings to be made there. Set points review, in our experience, is always a good practice to start with, to see if they're reasonable values, because often the building operation managers will change this to unreasonable numbers. And that may actually point to a fault of some kind, mechanical issues. Why has that set point been changed? So that's the first, basics, get everything out. Once that's been cleared, then we can go and interrogate the data. And we do it in iScan. It's built to analyze large amounts of building data in a number with several visual types. So it's summaries, distribution charts, and time series. And the way they work is that we can select values that we want to look at, and periods. So there's a lot of flexibility in that. So I just have a couple of examples here. So one is a heat map. So that one is it's actually two different sensors, one at the top and one at the bottom. I don't know if you can appreciate that it's two different heat maps. It's 5 months period, and we can look at it to look at patterns, hotspots, and notice if there's anomalies showing up. And another one that it's a very helpful view is this daily profiles overlay. So basically what this does is, this is a main electricity consumption graph, but basically we're looking at the average energy consumption by selecting, for example, a week, a month, weekends, or weekdays, and so on. So it automatically calculates the average of that period. So it's very useful when doing this kind of auditing of the energy consumption to detect if there's patterns, if there's spikes, if there's something that's throwing off the building performance. And there is then there's a feature that we call insights. So there's a few of them. I think specifically the two I wanted to show you are, one is the data gaps, very common. Data is not collected, and it's not stored for many reasons. Connection issues, sensors run out of batteries, that happens all the time. So this is a boiler return temperature, for example. This data, this is from an example from a project we had. And so this orange stripe is when there was no data. And I don't know if you can see that at the bottom, that was actually almost 60% of the time there was no data. And of course, as you move the viewing period in the software, you can see that. So this is also a very quick way to identify where those data gaps are and help you then go and chase and figure out what's going on. Set point tracking is also a specific feature by looking at when values are out of range. So again, the same boiler return temperature. There's a range, let's say 65 to 75 degrees, and we can check how often that sensor, the temperature is out of range. And so is it below or above? So in this case, for example, it was 28% of the time it was out of range. And this is an initial quick assessment that we recommend doing just to get a sense of how the systems in the building are performing using those very specific data points to extract. So basically, what we do is, you get the data, you find it if you don't have it, and you clean it as much as you can, then you can analyze and visualize it in iScan. Then we can publish it. So basically, when you're publishing it, you are using the data and those visuals to create a narrative, and telling the story of the building. If that one building could talk, what would it say its issues are? So the end objective of this is to try and figure out what is the story of those buildings' issues and help surface those to the owner, to the client, and say, okay, you can now make better decisions on your building based on that information. So this is a practical example on the University of Glasgow, just to show you how that initial step would look like, right? This is how in our experience, typically these kind of projects go. So in this case, they've started going in, getting data. So the first thing was just looking at, even before starting getting the data out, we started looking at what meters they had. So what data, how many data points they had by type. So this is an initial quantification just to get a sense of what was there. So this was almost 3,000 BMS points. And universities in the UK in particular have a lot of data points from that perspective. And almost 1,000, not 917 energy meters specifically. So that already gave us an idea of what we could look at. And of that energy data, then we'll put it into a Sankey chart, and you can see how big the electricity consumption is. So that already says something about where to focus on. So that electricity consumption is the first one to look at in terms of making gains and savings. So in this case, there were sub-meters. So those 520 megawatt hours, where are they consumed? So with that Sankey, we saw the first thing is that 46% of the consumption was not measured. And then that many electrical meters are actually not working. So this was already a starting point, and it seems like a very basic thing, but it allowed us to just go back to the building owner and say, these meters are not working. Like, you need to start, like, these are faults that you can fix. And there were meters that had working sub-meters not working. So like the sub-meter reading was higher than the meter reading. So you actually have, there's an issue in the metering itself. So this is very basic stuff to make sure that the data is reliable, because if you don't then make decisions, like if you don't have reliable data, all your decisions are going to be poor. So this is the practical work of that we usually undertake with actual buildings to make sure that the information is good. So that is the very first thing, gather the data, supporting documentation to make sure and make this critical reviewing of that data, analyze it in iScan. It is an iterative process, so it can be improved, but this is that tying the shoelaces before you start running. It then enables us to move on to the next stage. And that is the dynamic modeling of those retrofit interventions. So that is then when we move on to using that data to bring it into dynamic simulation and use it to increase the confidence in making design decisions when retrofitting a building. So this, if you are familiar with IS, you may know this. This is our bread and butter. It's dynamic simulation. So it is, so basically the objective is to make sure to identify the most impactful energy saving measures and make the most value of an investment in a building, right? And usually public commercial buildings in particular, they have an energy performance certificate that, so it might have already been done with an energy model that can be reused to carry out a retrofit analysis. So in this case, and the difference is that like the one plus of working with an existing building is that we have an existing building, so we can understand a lot on how the building is actually used and operated. So from those meter readings, once we know that they're clean and trustworthy, right? Talking to the occupants, talking to the building owners, then we can actually understand how the building operates in the real world. And when we then use that to make accurate energy models to predict the performance better than a compliance model. So we make calibrated energy models, so that helps then the designers understand where the actual design is. The actual energy demand is, and where the opportunity for savings are. And this usually helps evaluate not only the energy performance, but also the thermal comfort, because that is core concern of the building owners, of course, is to make sure that there's no negative impacts. Overheating is a common one in retrofit, as you all know. So the objective here is also to assess not only energy reduction, but only CO2 savings, operational costs, and on the retrofit project. So, and this is another use case I like to show you from the University of Edinburgh. And in this case, we look at a number of buildings on their portfolio. So, and this was, I think, an interesting example. What Kelly was saying, we had a building from 1878 in this project and one from 2018. So it was like the full scope. The uses of the buildings were very different. So some were, your typical teaching facilities. We looked at the library. Some of them had labs in them, so laboratories, which have their own complexity because the energy used there is pretty specific. It's not standard profiles of use. So what for each of these, then we did this calibrated models. In the newer buildings, we were able to use the EPC models that had been created, so it was a bit faster. And there was digital records instead of having to go with paper or doing on-site data collection. And they also had more, of course, sub-meter data that gave us a really good understanding of where the energy demand was. But then we were able to use that to identify where dominant energy demand was in the real buildings and where was the greater opportunity for energy savings. And these were very close models. I think, sorry, that you see that blue and yellow line is the difference between the measurements and the simulations. It was pretty close, very good calibration model from that perspective. So the interesting findings on this one, also using some metered information from the electrical loads, their scheduling and the occupancy, incorporating that in the models. We had a model that was a lot more accurate than the compliance modeling that you would do for an energy performance certificate, and really get to minimizing the performance gap. So the main ones, the main differences, how the actual building performed compared to those compliance models was, first of all, the occupancy. The occupancy was 3 to 4 times higher. And the lighting load in the compliance model was drastically underestimated compared to actual operations. And these differences really had important difference in the heating demands, the hot water demand, and overall in the energy consumption. So having those profiles was very important. And this was actually the comparison. The one on the left is the projected energy demand from the EPC, and then the calibrated model and the data set are the other two. So you can see how different that is compared to the real consumption and the predictions of the calibrated model. So the model then actually reflects the real world demands, and that's what you need to then use to make renovation decisions and retrofit solutions and choose retrofit solutions, because it enables you then to choose options that could have a significant impact on overall energy demand instead of basing it off the compliance model that you can see how the HVAC consumption is really tiny compared to what actually is in the building. So I'm not going to go into much in detail into this, but basically the way you approach this is follows an ASHRAE guideline 14. It's used by the ESCOs about everywhere on the building retrofit market for project financing. So the concept is that of a calibrated model. So it's an energy simulated model that's realistic and reliable. So there's some specific metrics that you need to meet on the variation and the error of the model. So the thresholds are pretty challenging to meet, because it's not just averages, it's also the scope of variation within the values. And you can look at the monthly or an hourly level, provided you have some actual data to compare against. And so the models we're talking about here for Edinburgh were all fully calibrated against this guideline. So it then we could then use it to determine, go in a very detailed breakdown of the energy demands of those buildings. So what we did then is, so there's a feature in the virtual environment software that's sub-metering, and that helps look in the energy demand and really understand where the demand is and where are the greatest opportunities to save energy. And then that in turn helps us identify and explore the energy conservation measures that are most likely impactful in reducing the demands, right? So in this case, then we looked at a broad range of energy conservation measures, simulated them on top of that calibrated model. So looking at improving building envelopes, upgrading lighting systems and the sensors, improving the controls of the HVAC, but also reducing the power to fans, adding heat recovery, which is a big one, and then looking at low carbon heat sources to minimize CO2 demands. And then also we looked at whether there were opportunities to introduce renewable technologies in the buildings. So overall, this was the result of those, so you can see the air source heat pump, the building fabric intervention, PV, lighting upgrades, and the columns are by building. So there's base, SCRM, Rosen, every color is a building in the site. So yeah, this is just to show you high level what that result was, that we could identify which solution would be most impactful per building on CO2 reduction and operating cost reduction. So that helped set realistic design targets for retrofit and identify which solutions are worth pursuing and which not. So in some scenarios, they would need several retrofit upgrades. So for example, in one case, if they wanted to add an air source heat pump solution, it would also in turn have a reduced operation temperature on the hot water loop, and that would then have a higher an issue in the capacity of the heat emitters, like the radiators in the building. So it would also need an upgrade of the radiators to end the heat source to accommodate that air source heat pump. It may also come with an improvement of the building fabric and the air tightness to minimize the heating loads and ensure that that air source heat pump upgrade, which is now a very common retrofit solution, is successful. So, and the other side of that is when you have a natural ventilation, you also want to make sure for the summer, you want to make sure that your retrofit solutions don't cause overheating issues in the summer, because that's something that across Europe we're seeing more and more, that as you make buildings more airtight, you improve insulation, but then you're trapping heating in the building, and that causes unwanted overheating and thermal discomfort. And that's something we do not just with the simulations, not just for the present, but also with future weather files. So that's something we're finding is always more and more important to do, is to look at those calibrated models using the future weather to make sure that the design is safe for future as well. So yeah, our best practices and takeaways on this is the first one is model accuracy. So existing buildings have those challenges on the data, yes, but also give an opportunity to have an accurate model because there is some way of gathering that current data on the operations from measure system, if you're lucky, or inferring information from the occupants is a big source of useful data. Then the calibration then helps confirm and verify the model is an accurate predictor of the future energy demand. And then with that, you have confidence that the retrofit solution that the design team chose is going to be the most cost effective. And it also helps mitigate risk. So using that dynamic simulation helps to figure out that there's not going to be unforeseen issues, or you can flag it early enough that it can be remedied before it actually becomes an issue in the actual building. So on that, just let's take a moment to discuss maybe what technologies or measures do you think will have the greatest impact? This is not something that has an answer, I think, but I think it's a good one to discuss as on the decarbonization. Any favorite technologies, measures on insulation?
Triple glazing.
With all this, yeah, it's the most expensive one.
Monitoring and control.
Mm-hmm.
Checking the set points.
The curve set points. Other favorite?
Energy sourcing. I mean,
Yeah,
it's,
yeah, decarbonization of
People in general, occupants.
occupants.
Or
Occupant behavior. No, it's 100%. 100%. Yeah, I think that actually covers everything.
Integrating renewable energy.
Say again?
Integrating renewable energy.
Yeah, decarbonizing. Yeah, sources. Yeah, yeah. So we can see. Let's see how what we do when we've done those things, right? Because these are all things we can model, but then we need to make sure that they're acting as they should, right? So we put those recommendations, those ideas in the model, we test them, we see what the impact is, then we go and monitor and track that performance and do that monitoring and verification. Because you have made an investment, you want to make sure that you actually get a return on that investment. And so the question is then, I've done my retrofit. Is my building performing as it should? Did I get my savings in energy, carbon? And what do I do next? What's my next step here? So it's like, if we go back to the marathon idea, right? This is the end of the run, of the finish line, but you want to make sure that you understand, okay, you've recovered properly, you're ready for the next one, and you're ready to go, right? So we believe that the energy model helps in that journey together with measured data and to improve that fidelity and help make additional decision. And that when it really becomes a digital twin, because you can then use it to compare that optimal behavior with the actual data, and you actually track the savings of this retrofit projects you invested in. And this is when then you combine the energy model. So with those physics-based principle, there were already some measured data there to make it, to calibrate it, but then the next step is linking the live data to the model. And then we use that to show the optimal behavior that the building should have. And then we're also using some AI and machine learning, not to create data-driven models primarily, but to do data-driven prediction, to fill those data gaps that we saw are huge. So there's a lot you can do with machine learning and AI on that, and to detect anomalies. Basically, we get that physics-based live data AI meld together for a performance digital twin that really behaves like the real counterpart. And with that, you can make investment-grade decisions and operate the building more efficiently. So basically, what you then do, just to bring it all together into one timeline, like looking at an existing building, we start being able to answer, how has my building performed in the past? So look at historical data and the data analytics. We look at the past and the present. Then the question is, how is my building performing now? Is there any drift? So we use live data that flows from the building. We leverage the data analytics. But then the question is, how should my building perform? So not just how it is performing, but how should it? Can I make it perform better? There are easy wins. So there are operational adjustments to implement to make it perform better. And then look in the future. What should I do? And how's my building going to perform in the next 10 or 20 years? Can I reach net zero? Can I ensure my investment delivers against my target? So it's all leveraging at the core, the energy model and simulation. It is a combined approach. All these aspects together make a difference in renovating the building stock. And the most recent tool that we launched in this is IS Live. It's an online data platform, and it has together the live data from the site, the digital twin and simulated data from the model. And so basically, it uses the digital model over the whole life cycle, right? It supports that ongoing optimization of energy and costs. Like you can see how the energy is used and in that identify if there is that performance drift. It also helps in looking at previous renovation. So if there's been a refurbishment, you can verify the energy cost and carbon savings of those interventions and then report to different stakeholders. And this can also help when you're dealing with stakeholders that are not necessarily super technical, like they don't necessarily know what an energy model is, but they can still use the outcome and use it to optimize the building on a daily basis. So, for example, there's occupancy linking to energy use. So this is something that was a very hot topic during COVID, is the use and cost per occupant of buildings, but also monitoring the indoor air quality, like CO2, the temperature, the humidity, and looking at the comfort. And I will show you an example of that as well. But basically, the value case that we find for this approach, for that performance digital twin approach, is that it helps make the most of all the previous work. So you've done the modeling, those investments, you keep using that over the course of the life cycle of the building. You've set up your data connection. you're always using that and reinvesting that intelligence into the building. And to manage the risk, to have high-level reporting, and it is eventually a digital asset that helps a year on year to figure out if there's new savings to be made, to monitor the success of previous projects implemented. So on this, we have a really good example in the University of Liverpool. This is same thing as the University of Edinburgh. Like they came in asking for assessing a potential retrofit project, and this was the foundation building. They wanted to do HVAC refurbishment, install LEDs, and implement demand control ventilation. This is a pretty common, a set of renovations. And they want to know, okay, what's the potential impact? So calibrate the model, first of all, so the data collection, everything else went in place there. So the estimate through simulation was 14% savings after doing this intervention. So they went and they did the renovation. They actually refurbished the building. Then after they reopened it, they came back to us because they had invested into building that model, that digital twin. So they wanted it used, and they asked us to upgrade it to that performance digital twin and actually look at, first of all, what were the actual savings they were making from the refurbishment, and then use the model to look at future decarbonization scenarios. So here, that data from the building management side was connected live into iScan and then IS Live from the meters as well. They install sensors on the lighting to look at occupancy, to get insight into that. We connected all of that information in the model, and now this is being used for efficient operations, monitoring of the renovations, and then to assess the potential additional interventions and create a decarbonization roadmap. So this is a screenshot you can see here of the overview page in IS Live of that data connected in for this specific project. So there's an overview of the overall energy use, breakdown of the energy consumption. It's a bit tiny. Breakdown energy consumption, electricity in different uses, and a comparison of the prediction against the digital twin. So that's the drift that we can look at. There's also on the left-hand side, there's indoor environmental quality variables. So there's temperature, CO2, and humidity in different spaces. And there's also a view on a floor plan of the building, so people can go and spot anomalies. It's color-coded as well. And there are key performance indicators in real time that can be looked at. And because this data is dynamic and it's real time, it is not a static picture. And it can also be interrogated at different scales. So it can be looked at, for example, a full year or 48 hours. Depends on the kind of question you have. Do you want to see an annual performance? Do you want to see operational day-to-day issues? So specifically in this case, we went into that, monitoring and tracking of the impact of that refurbishment project. So we used the existing model, so the baseline model before the retrofit, the calibrated one that was used to design the renovation, and that this model is now running on the cloud regularly, and it's plotted. It acts as a baseline, and it is plotted together with the measured data. So we actually see the differences there of the savings of they're being achieved. So this is like the first 9 months of operation of the new HVAC and LED systems. The savings were up to £25,000. So that was on those 9 months about 23% of energy savings. So, and it keeps being updated. And of course, this was a few months ago, but this keeps running. So they always can see how much they're saving. And in particular, they found this helpful to go and report to the management of the university, to the CFOs, to the financial decision makers, to explain, okay, the investment is achieving the goals we're expecting. These are the actual savings that we're getting. So this, from the user perspective, from the people who actually did the renovation and carried it on, this was an important feature to be able to support the business case for new interventions, for new retrofit. So that visibility is important to then enable, let's say, a longer term commitment to renovation. So this is another example. There's another couple of examples on how we use digital twins in IS Live. So in one is, you see there's two curves. So one is the meter data and the simulated energy use from the digital twins. So it's very, very close. Basically, the use of these charts is to identify if there's performance drift. So is there some new issue that it was detected before in the initial phase where you're looking at the performance gap and the model was very close to the building? If those two started drift, like the model runs with the same weather data that's in the real world. So something is happening in the building that's not accounted for in the model. So how is the performance of the building drifting? And so that will tell you immediately if there's some issues to look at. You can look at the costs, the energy use, and the CO2 emissions as well. And the other feature is actionable intelligence. So it's actually strategies that you can implement. These are typically operational strategies, and it's looking at is that baseline versus proposed screenshot there. So basically, through this interface, you can propose some potential savings on, for example, you want to change the set points on the heating and cooling. You want to change the schedules of operation of your HVAC, and you can then forecast what the savings are going to be. So it's not a big investment cost, but it can be an important savings in energy and cost savings. So then that gives you a view of what you could do, and then you can go implement it and track it, monitor and track it. And this is something we are actually doing right now with the University of Liverpool. So in the end, what it comes down to for us is closing that circle, right? So you have invested into getting an accurate energy model, getting a lot of data, and on the whole life cycle of the building. And so then you start from the design of the retrofit intervention using that model. Then you calibrate it, and it helps also understand better the buildings through the data. Then you couple that live data with the energy model and get to a performance digital twin that can become a long-term life cycle asset to improve the performance, and it's leveraged for future decision making. So in the end, the way we see this is that verification, and we see it from the end users as well. In all these cases, that's the biggest learning for us, is that being able to prove that the retrofit was effective is fundamental, because then that helps unlock further resource, additional investment. It talks directly to the fact that there's the renovation rates are low, because the decision makers need to know that they got the benefits that they wanted out of the renovation. In general, this is crucial to globally to improve on our decarbonization journey. The other important learning and takeaway is that performance optimization is not one-off. It's a continuous process. So the energy models and data should be set up in a way that can be used continuously to provide that feedback, to get those good feedback loops, to inform future upgrades, optimize the performance on a daily basis. And the core focus is using existing assets as much as possible. So as you use those energy models, you have created those energy models, the building owners, through their designers, they've been investing into those. So they should keep using them on the whole life cycle of the building, because it's been a lot of effort to go and create them and get the data, So it's not just to make a renovation and a retrofit design. It is for that overall life cycle of the building, unlocking operational savings and having the ability to make those investment grade decisions and risking the future. So I think this is my last slide. In fact, I'm sure you will all agree that every building can make savings. I think that's the experience we all have in the real world, right? But the core challenge is just getting that data and analyzing it, because the savings are there. So we just need to figure out, first of all, where it is. So the strategy is in three stages. First one get the data, understanding where those low and zero cost savings are, first of all, by operational optimization. Then you can move into dynamic simulation modeling. So, and going into that investment grade decision making, testing those retrofit measures that can have an important capital outlay, like HVAC upgrades, fabric improvements. Then you can see what can be done to improve further and refurbish the building. And the ultimate objective of this is empowering the building owner to monitor and track the performance continuously using that performance digital twin. And then they can make the best decisions on the future capital spend, understanding the impact on scope 1 and 2 emissions, and facilitating accurate carbon reporting. And that's it for me. What I want to also, if you want to see more of this, we have also put out an extensive guide on the website at that address. Has more details on these use cases as well. And yeah, that's I think that's it for us. Thank you. And if you have any questions, I think we're happy to take them.
I have a lot of questions.
Oh, Jesus.
But great job. I liked it. But mostly, well, first of all, I think it's a great tool. Mostly just out of academic curiosity. I'm looking a lot into life cycle assessments. So you mentioned decarbonization a lot. What methodology are you using to count your carbon? Is it LCA?
This is only operational carbon emissions. So it's based on the carbon emission of the
energy source of the energy. Okay.
Although you can connect the email to one-click LCA.
Yeah.
Okay. And then in the retrofit options, of course, you have a lot of slides now. I'm trying to pick up. When you say, for example, you will save, there's a 14% energy savings or decarbonization potential. Do you include into that the embedded impacts of the new material that you will buy?
No.
So purely operational, yes? Because it depends, what insulation you buy, combined heat pump, what refrigerant you use, and so on. So that's another thing that
no, 100%.
makes
I
a
think
whole
you know
difference.
this better than I do.
And for the money is the same, I suppose, right? But obviously, if they're already saving quite a bit every year, they have to make a decision if it's worth investing in the new equipment. Okay, yes. And then, yes, one more maybe. When you establish the baseline energy simulation, for how long do you need to monitor a building, would you think? Do you need a full year data or
ideally,
typical seasons?
it depends. I think it depends on what your interventions you want to look into, right? So if you want to look at whole year seasonal, like heating or cooling savings, you're going to need at least 1 year measured data to compare against. You can do it usually we do it on a monthly basis because it's very hard to get sub-monthly data. You have your energy bills. So that's the first calibration you can do, the monthly. But if you want to optimize, say, indoor comfort, then you need to look at hourly. But you need a shorter period of data collection, and you do calibration that are more specific, like, I don't know, your summer, you want to look at overheating.
And then how fast would it be if this is your business model? Let's say IES comes to a new university building or like if they ask you, okay, guys, we want to do the digital twin, like how fast can you do it? Because I don't think it's easy, of course, but on average for these case studies.
I think these are actually colleagues that prepared this said some of them were a few months, but because of the back and forth that's required. It's not the building, the models itself that takes a lot of time. There's a lot of space and time needed to wait for that to get
To respond and to give you
Yes.
the right data and then to correct and to
Yes.
And actually, there are a level of details for digital twin. So you can create a digital twin when you have only 1 meter data, so 1 temperature sensor. So you can already start creating a digital twin. I take an example of manufacturing process inside a big warehouse. They replaced the machinery, so they changed entirely their process, and there was mechanical chemical and electrical heat release. So they couldn't just put a meter to measure it. So they had, just for 2 weeks, temperature sensors and a weather data on the rooftop. So they created, so when I say they, that means the clients, not our consultant. They created a V-model with all the constructions, geometry, etc. And they took this temperature, and inside the V, they didn't set it as internal gains, but as a heating set point. Because the heating system was turned off and they had warm enough temperature in winter. So they
It's
took
all the
it,
machinery.
yeah, and actually from the V results, so the heating load to match this temperature was actually the heat released by the machinery. So that was a digital twin, and they took this this curve for 2 weeks. So we had a very nice pattern, so which was very obvious. They just looked at for the rest of the year, so that they could size the cooling system for the summer. So, and they had to do it very quickly because they witnessed this overheating in winter, and they wanted to have the system in place for the summer before the overheating. So digital twin, 2 weeks of measurement, one channel.
Well,
So
They're very controlled conditions, I imagine. It's a factory floor, right? So you know that you operate the same way, so it would make sense, I suppose.
yeah. So
Yeah.
the digital twin is a buzzword. So it sometimes needs to refine it, what it means.
Yeah, it's very unique and bespoke. Like every building, you need to figure out exactly how you apply it. So you can't just go in and say, give me all the data. That never works. Never works.
That's all my questions. Thank you very much, guys.
That's very good questions. Thank you. Anyone else? Yeah.
So just again, a question about the digital twin. So basic version of a digital twin for a building is have the temperature sensor and understand the power consumption per section. These are the typical data that are
Yeah.
needed to create a digital twin.
Or now more and more in Europe, you have the power demand every 30 minutes. So if you take that, you can already start to have a digital twin because if you have heat pumps, lighting, etc., you can start calibrate your model. So in sub-hourly data, it's already very fine. So
So it's like a data per equipment, what each equipment is consuming.
yeah,
That's
so
about.
if you have sub-metering,
Okay.
then you may know what comes from the air conditioning, lighting, etc. But yeah, quite often we still have digital twin based on monthly data. That's a nightmare because errors can offset each other. So if you have hourly data, daily data, that's fine.
But that's when, if you need to make a decision at that level, then it's worth, from the client, it may be worth making that investment of monitoring a specific meter. You like add a specific meter to get the data out. But first you look at it from the point of view of what's the breakdown of consumptions, because then it's worth then making that decision of, okay, I'm gonna actually monitor this one, I'm gonna add clamp on meter and get the data out because I want that actual data, more accurate data to use in my investment. So that's why it's iterative and it's not like linear, because you find new things as you go in this, and then you decide where to go and invest more in data collection as well.
I mean, just a comment, sorry about this comment, is about the terminology. If you're just reading a meter once a month, why do you still call it digital twin?
Meter once a month, because it's not the meter, it's a performance-based model, the core of it. So there's a physics-based engine. So that data goes in the calibration. So it's not, we're not just taking in that meter or the energy bill. It's the 3D model with the physics simulation at the core of it is matched to that demand to make sure that the physics model, that the 3D model has an accurate prediction. That's why it's called digital, because it is actually that.
So it's more complicated than this.
Oh yeah.
Yeah. And yeah, just something we never mentioned here is that when you have metadata and a VML or digital ML, of course, you need to use in the virtual ML the actual weather data from that year where you have the monitoring. So climate data are also very important. So you have to take the right data for the year of the measurements for the energy consumption.
Closest weather station.
So sometimes you can just place weather data on the roof, or you can buy. So if you have a weather station close, you can just pick.
No, and that's something. That's also something that we have that in iScan, and we use it a lot. Like we have also weather data service that we use for this a lot, because you really want to know for those coordinates what's the actual weather that's been recorded. It's very high granularity, because you need that to simulate accurately, because otherwise you're not going to compare to real measurements. It's not going to make any sense. So. I do appreciate it's 5 p.m. So but look, we're around tomorrow, so if you have any more questions, you can come and grab us. Myself, Leon, anytime. Or, well, Andrea as well.
Do you guys do any free digital twins now that you have a stand here over the?
Yeah, just the desk and sort of the door.
Or come see my presentation to my paper tomorrow on using a comfort digital twin at an airport. So.
Bring my building model and you can digital twin it.
Oh yeah, no, not me, someone else. Well, thank you everyone, and we'll see you at dinner.
Do you mind if you go back just one slide?
Sure. Oh yeah, sorry. There. Oh.